My name is Benedict. I'm one of the co-founders and the CEO of Synple. We are based in Zurich, and we came out of ETH as an ETH spin-off company. For the webinar, we have basically two topics now. First, I'm going to give a short introduction to the Synple system, give you some more detailed explanations on how the setup works step by step. And then I show you how we can make a small library of quality leads quite quickly with our machine and with only minimal physical presence of the actual chemist. So let me dive right in. I can change the slide. Yeah, in the recent years, there has been quite a growing drive and interest towards automating chemical synthesis because it has the potential to actually increase efficiency and output of chemists and at the same time lower costs and increase safety in comparison to the traditional chemistry synthesis. And the current approaches towards automating chemistry mainly focus on flow chemistry on the one hand, and which include continuous flow chemistry and self-optimizing systems. And on the other hand, more robotic systems based on liquid handler 96 well plates. So if that has like such a big potential, why are these systems not already being used everywhere? Or what is holding us back? So one main point is that available technology is still quite limited to specialist groups due to their complexity and costs. So most of the time, it requires expertise in software, engineering, electronics to run these robotic systems. And there's also been some examples in literature who show completely in-house built systems. They're often great at what they're doing and quite innovative for the application. But of course, not every company and every research institute has the team or the resources to put something like this together. So the everyday chemist's access to automated technologies, therefore, is still quite restricted, especially for discovery chemistry, where the main driver is just making the new compounds for testing as quick as possible. With the exception of the specialist technology groups, most of the chemists working in this field do not really have the time to spend programming, optimizing and fixing machines for every new reactions they do. Therefore, our goal was to bring a technology to these chemists that was really incredibly easy to use, requires no programming, and offered the ability to do the reactions that they would routinely do, but in a fully automated way. So, therefore, like Synple has developed a fully automated synthesizer based on disposable reagent cartridges that works similar to a well-known coffee capsule system. The technology consists of the machine hardware, which where we now have 2 generations of synthesizers available, and then the pre-programmed reaction protocols, plus the reagent cartridge that come pre-filled with all the reagents necessary for a particular reaction. To set up the reaction, it really requires only less than 5 minutes, and I will show you the very easy process in a short video of our next, the first generation device on the next slide. Let me play this video. So the user simply inserts the starting material here in this vial that he would like to transform, and he picks then afterwards the cartridge for the particular reaction he wants to do. You just scan then the chip of the cartridge, and then the machine loads the pre-programmed sequence, and then you just insert the cartridge into the holder. Then upon the push of one button, the machine carries out the chemical reaction to generate the isolated product in a very short time and safe and convenient manner. There's really not much more work to do for this. Due to the simplicity and speed of running reactions on our technology, the advantage is quite clear. So it takes really 5 minutes of hands-on time, which would otherwise take hours manually. When the reaction is done, the user can just simply come and pick up the product, which will then be in a solution in the same vial. So as you can see on this slide, the dimensions of the machine is actually really small, so a tiny footprint. So it can be easily accommodated in a standard fume hood next to other traditional synthesis equipment or other technologies. Alternatively, we can also connect several units together to create like a flexible parallel synthesis setup that is controlled through a central console. You can see here at the bottom. And there you can generate like a small library of compounds, which I'm going to talk about later. The reagent cartridges here on the right, as I said before, they come pre-filled with the optimal reagents in 4 compartments, which are required for the reaction and the subsequent workup and isolation. The maximum capacity of these cartridges depend on the type of reaction, but is typically between something like 0.1 millimole and 1.2 millimole of material. Beyond this amount, the reagents in the cartridge have been depleted. And each cartridge then also comes encoded with the method required for this particular reaction. So you really only need to scan the cartridge and no programming is required. We have now at the moment a range of applications available. This ranges from more like standard organic chemistry like Mitsunobu reactions and fluorinations to more easy reactions like protecting groups, but also applications like for the PROTACs or for the biotin reagents where you can couple biotin tags to your compounds. They offer significant time-saving benefits and prevent the user from being exposed to toxic, hazardous, or dangerous reagents, for example, in the heterocycle formation. We are also constantly working to expand the available applications. So if you would like to know more details on the existing ones or the upcoming applications, just have a look on our homepage or send me an email. The new applications will then slowly appear on the homepage. So I would like to just give you an idea how the technology works inside the machine. So it's not just a black box. So I'll talk you through 2 of our current applications. For the N-heterocycle formation, you can easily convert aldehydes in the corresponding heterocycles. And we have several cartridges available for different heterocycles here on this side. And they range from different heterocycles from substituted morpholins or normal morpholins to 7-membered rings or even spirocyclic structures. To enable this, we have encapsulated these toxic organotin reagents here on the left as a solid supported form within the cartridge. We also have then in the second compartment a copper catalyst, which enables the cyclization. And then we have some SCX in silica, which is basically a filtering agent and a catch and release resin to make a simple workup purification. So how does this actually work? On the left here, you see a diagram of the inside of the machine. It mainly consists of 2 valves and pumps. The valves are these 2 circular things, and the pump. The sample vial is here. So depending on the valve setting, the solvent is either taking from the sample vial or the solvent and is then pumped through the pump and the second valve into the specific compartment of the cartridge. Afterwards, the solvent is then circling back into the sample vial. This is like the general process, how this works. But let's go through step by step for the N-heterocycle reaction. For the N-heterocycle formation, the first step, we add some solvent to dissolve the material in the vial, and then we constantly circulate the reaction liquid for several hours through the compartment, the SNAP reagent. So it goes up here, through the pump, and through this compartment for the time it requires. And during that time, it reacts and forms this imine. The advantage of having it on the polymer support, it does not really matter how much aldehyde you use, up to 0.5 millimole, because all the excess reagent will stay bound on the resin. So once the imine formation is complete, the copper catalyst is added to the imine To do this, some solvent from the solvent bottle washes the copper catalyst from the second compartment into the vial. This is then stirred and heated to enable this cyclization. And this also takes for this process a few hours. Once this is complete, the solution is then passed through this compartment through a plug of silica to remove all excess copper, and the liquid then afterwards also comes back to the vial. And finally, we load the solution onto this SCX resin. It's a catch and release resin where the product is caught and all unwanted materials are washed away. During that time, the vial is automatically washed before the product is eluted from the SCX back into the same vial. The solvent then can be easily afterwards evaporated to give you the product in approximately 90% yield purity. All these steps that you just saw are pre-programmed and happen automatically, but the user can also choose, if he wants to change certain key parameters, for example, the imine formation time or the cyclization time. This particular reaction has quite a broad range of aldehydes that can be used to get good yields for morpholins, for example, piperazines, diazepams, and oxazepams. Here I see a few examples. The reaction allows aromatic ones, heteroaromatic ones with many different functional groups. Slightly lower yields can be expected for aliphatic aldehydes or aldehydes with lower reactivity, for example, the paramethoxybenzaldehyde. But generally, they're all produced in good purity, and the yields are in line with the examples published in the paper, where they are basically synthesized manually. Here, I just want to show you quickly an analytical data of the product. This is how the product actually came off the machine without any further purification. And we are just adding some mesethylene for as analytical purpose as an analytical standard. In the LCMS trace, you can see basically apart from the mesethylene, there's only one major peak with the product, and otherwise it's mainly the pure compound. For the second reaction to quickly go in is the reductive amination. The user can, for this one, actually choose both the aldehyde and the amine. So you have a very broad scope of what you can use that for. We packed in the cartridge some solid supported reducing agent and an acid to facilitate the reduction. Also, we have two scavengers where we can capture any unwanted products or starting materials. It basically works similar to how I showed you before with the N-heterocycles by circulating the reaction mixture through the individual compartments for a certain time. Also here, the substrate scope for the reduction is quite big, and we obtain really good yields and purities for this. The example substrates we show here also have many different functional groups that can be also functionalized in another step, so that's quite useful. So I talked a lot about yields, but what about the reproducibility? Usually if reactions are carried out manually, often the reaction times between different runs don't really match because there are slight variations between each time a reaction is done. Maybe at one time of addition of a certain reagent, or the person is just at a lunch or a coffee break or meeting, or is simply stirred several hours longer because it's actually night. Also, sometimes there's variations between how different people carry out reactions or handle reactions. For our machine, it basically runs the exact same protocol every time. And if you compare in the scheme the yields and the yields for the same substrate, they basically match plus minus 5%. Yeah, it doesn't then matter whether the individual runs a month apart or whether the synthesis was set up by two different people, you will get similar results. So now I would come to the second part of the webinar, where I would like to talk about expanding the idea a bit more away from just using a machinal cartridge. We have now a range of applications or reactions available. And just like in the lab for multi-step synthesis, you can, of course, run transformations on the machine after each other and make kind of multi-step synthetic work and make these types of molecules that you need to have completely on the machine. So we wanted to show how the Synple machine could be applied to run a lead finding project and how this how you can do this basically with very little amount of hands-on work. For that, we first need to address that our device is actually not a high throughput device, where you just make millions of compounds and screen them. But making and screening everything possible isn't really necessary or useful today anymore. So to deal with this, why don't we come up with a virtual library which consists of all the possible molecules you could make with a Synple machine, based on available starting material and based on commercially available starting material and available cartridges that we have. If you have this library, this could then be screened against virtually against the target. The methods available are nowadays quite good. And then for this type of pre-selection, these methods, in silico screenings, are quite well suitable. After you have done the pre-selection, you will get a small selection of pre-selected compounds that are all more or less guaranteed that you can make them with the Synple machine in roughly 15 minutes working time each. So in collaboration with the Bodhi group at ETH, we have actually tried this, and Angus, you can see on the right, a PhD student with Jeffrey Bode has done most of the work together with Wilson. To start this, we picked our first two reactions we had developed, the heterocycle formation and reductive formation. And Angus developed some slight variations of the polymer supported SNAP reagents called iterative SNAP reagents or iSNAP reagents. The special part about these reagents is that they have here another masked ketone. So after the normal SNAP reaction where you make the heterocycle on the slower part, you can then deprotect it and have another functionality there. So what we then did, we ran the first cartridge with an aldehyde, and we will first form the N-heterocycle just like with the normal SNAP reagents to get this compound. In the same cartridge, we then use the acidic SCX resin to deprotect the acetal, so you get to these compounds. After the run, you then have a solution of the heterocycle with an unprotected ketone. And in a short manual step, the solvent just needs to be evaporated and the amine added. Then you just switch this, the cartridge, use the new cartridge with a new sequence, and start the reductive amination reaction. And this second run is just a normal reductive amination. So you get at the end these quite nice looking molecules. So this was the basis for then developing the virtual library. Based on these two reactions, Angus then put together the virtual library and used 4 of his iSNAP reagents. He picked 195 commercially available starting materials that we actually had also in-house, and he picked 169 amines. After filtering down these 460,000 compounds that you get based on the Lipinski's rule of 5, you then get around 300,000 compounds in total in the virtual library. These are quite good, rich in sp3 carbons, and they cover most the lead-like and drug-like space. Because of the substitution pattern of these iSNAP reagents, the library was quite biased towards the rod-like shapes in the PMI analysis with quite a higher plane character and only a few trending towards the spherical type. So this is something we could in the next step work on. This library was then screened by a collaborator, and it returned 5% hits, which is still quite a little bit too much to make them all, but Angus handpicked the best results to also cover some of the space here. which were then synthesized on the machine. So you can see each of these compounds here takes really only about 15 minutes working time to make, and the yields are ranging between 20 to 40% over 2 steps. And also you can also have several machines running in parallel, so you can obtain these compounds within a few days if you want. There is really no more hidden working time where you first need to program the robot over several days or set up a sequence. This is all done by us. In terms of yields and amounts, the aim here is just to get some material to do then the biological testing to confirm the results from the in silico screening. And I think Angus has sent the compounds already for biological testing, and we are currently waiting for these results to get back. Actually, the library itself we can give that to anyone. It's free and available for download. There will be soon a link on our homepage, or just send me an email, and then you can just get it from us before. Then you can already run your own in silico screening and talk to us if you find any nice leads. We're also working on cartridges for example, amide bond formation, where this concept could be, for example, also expanded, since these compounds have still a free NH site. So you can imagine to expand this library even to more compounds by adding something to this other handle here to increase the available chemical space further. So I think this was just a quite nice example of the potential application, but there are of course many more applications that you can use this tool for, and we're really happy to discuss the potential applications in your lab as well. I would like to open now this for questions, and yeah, thanks very much for your time so far. So yeah, if you have any questions, just post them into the Q&A window, and then we can answer them. Or if Paula, if you want to add anything, then please go ahead.
Yeah, no, I think you covered everything quite clearly there. I think maybe one of the future plans that we didn't touch on was expanding to all the virtual libraries to all our available reaction classes. So at the moment, this virtual library just focuses on the SNAP chemistry and reductive amination, but the plan is to expand this further.
Yeah. Okay, we have one question from Dietrich Böse so he says, thank you. Can you comment on the diastereoselectivity selectivity of the SNAP reagent? Yes, we have. I go back to this slide. At the moment, I know that basically we don't really know what guides the diastereoselectivity. Angus has tried to separate, and that was successful on the HPLC. You can separate the two compounds, and then you have basically two sets of compounds. I think there was also a paper from Jeff where they tried to make these enantiomerically pure, or like diastereomically pure, with instead of using the copper, a normal copper catalyst, they used an enantioselective copper catalyst. That was not very successful. So I think you need to come up, you will end up with these two diastereomers. The next question, the cost of the machine. Yeah, we have actually two models for this. We can either provide the machine for 25,000 Swiss francs is the list price, or we can give them to you on a pay-per-use basis, mainly more or less for free. The only difference will then be the cost of the cartridge later. if you decide to purchase the machine for the 25,000, then you can get the cartridges afterwards for half the price. But you can, if you want to just try it out with the pay-per-use first, you can still switch later to the buying model. It's totally flexible. The next question is, can the cartridge be reused? No, they cannot be reused, unfortunately, because most of the time then the reagents inside the cartridge is just used up. Based on the environment, we have seen so far that when we actually use these cartridges, we use less resources than what a chemist would do in terms of solvent or for extracting and so on later. So we have, our calculations show that there is basically a lower impact on the environment when using these cartridges. But we want to offer later a system where you can send them back and we can recycle or reuse certain parts and fill new material in. The smaller scale and the larger scale. First, I go to larger scale. It depends on the cartridge. So for the block protection, we can go up to 1.5 millimole. For the heterocycles, it's roughly 0.5 millimole maximum. And for the applications where you usually don't need that much material, like the Pro tag or the biotin tags, it's maximum 0.1 millimole. However, having said that, there is then really no lower minimum. You can, because most of the reagents are solid supported, you can then just use less amount of your starting material. Okay, yeah, that's for that. How do you deal with the waste from the SNAP reagents? The waste from the SNAP reagents, all the waste that comes from the machine is basically dispensed into a normal glass bottle, which then you basically can just screw closed and send to your waste disposal stream. Otherwise, the other tin waste, that is all then still contained in the cartridge. So in total, all the toxic tin waste will still be either contained in the solvent bottle or in the cartridge, and you don't really need to physically touch it. You can just you can just bring it to your normal waste stream. How many compounds did Angus make? Yeah, so he only used one machine, therefore it took a bit longer. However, he also had to develop this sequence for running these ones. I can ask him later, but if he would need to repeat all these compounds that he make, he would probably be faster. Just like now, the sequence is set up, and that's what we also usually offering to our customers, like the finished sequence, so that the customer don't have to deal with programming these machines themselves.
Sorry, just to add to that, I think it probably takes on average 24 hours of machine running time to make each compound.
Yeah, but it's running completely automatic, yes.
Yeah, exactly.
Yeah. So the temperature variations, usually the machine can go up to 80 degrees of temperature, but really the user doesn't really need to take care of this, doesn't really need to look at the temperature because that's handled all automatically. Again, of course, if you would like to change or alter the pre-programmed reaction sequence, you can, as a user, go into the system and change settings. Shipment of tin containing reagents might be difficult. Yes, that's true. However, the amount that we have in the cartridges, they are considered for shipping small amounts. So there is actually no problem. It would get if you have actually shipped the if you would need to ship the snap reagents like on a 100-gram scale in one bottle, like Sigma-Aldrich does, then it would get more difficult. But also we have a license for shipping dangerous goods, so even that it would be possible. Is the footprint the only difference between the two machines versions? No, the new machine has also some more functions that some more software functions. For example, you can change the parameters on the for each reactions. So it's basically the newer model. Can you comment on substrate concentrations? So when you set up a reaction, you have a certain sheet where we can give you tips of how to set up the reaction and how the concentration of your starting material should be, and that's quite useful to follow this. Yeah, at the end, the concentration depends on the reaction. Are there any ways to circumvent poorly soluble starting materials? So yeah, this is one limitation, that of course your starting material has to be somewhat soluble. However, in the application notes, we give you hints towards what kind of starting material, what kind of solvents or co-solvents you can use in the reaction for less soluble materials. But yeah, if you have really a rock which is absolutely very badly soluble, this is one of the limitations. The time is also adjustable, more flexibility for customers. If I understand the question right, it's, yeah, you can adjust the reaction time. So if you think the reaction time that we have set for a standard reaction is too short or too long, you can of course change that. And Angus asking, is it possible for us to develop our own transformation or applications for the machine? Yeah, thanks for that. You can, of course, we have certain programs with customers where you get a special cartridge and you can develop your own transformation for the machine. Just send us an email if you're interested, and we can talk how we can facilitate that for you. So yeah, I think so far I've answered most questions. Yeah. Paula, do you want to add anything? Or?
Did you answer the question on cost?
On cost, yeah,
yeah.
I talked
yeah.
about.
Okay,
so,
sorry.
Yeah, otherwise, then I thank you very much for joining. We should have another webinar in somewhat 1 or 2 weeks time, hopefully. And I hope to see you again.
Sorry, Benny, there's one more question.
So that's okay. Possible to guide customers with some simulations to determine the stereochemistry. We haven't done this so far, but I know that Angus did some simulations regarding the stereochemistry, but I don't know the details. So if you would like to know more, just send me an email what you want to know, and then I can discuss with Angus a bit closer. Okay, yeah, then
sorry, Benny, there's another question regarding cartridge price.
Yeah, the cartridge price is so as I said, when you buy the machine, you get 50% reduced price on the cartridge, but they're roughly between on basis of the 50%, they're roughly between 50 francs and 150 francs, depending on the type of application. So the easier types of reactions, like the Bock protections, for example, they range around 50 francs. If you want the Protec cartridges or the Biotin cartridges, which give you a bit more complex reagents, they lie around 150 francs. the shelf life of the cartridge and the storage condition. So far we can guarantee shelf life of up to 1 year. And because we store them in special bags, they are totally sealed away from any moisture or oxygen. So yeah, they can be stored up to a year, mostly at room temperature. Some of them have to be stored cold though. Cartridge can be reusable and washable. Now, unfortunately, you cannot reuse the cartridge because the reagents is then used in the cartridge. We have a washing cartridge that you can reuse as much as you want to clean the system. That is reusable. But the other ones, the reagent cartridge, unfortunately not. Because, for example, in the heterocycles, the copper catalyst or the SNAP reagents, they would be used up. Okay. Yeah, then thanks again for your time. I think we are at the end for today, and I hope you stay safe, and I wish you a nice afternoon.
Okay, and if anybody has any questions later that they think of, then don't hesitate to get in touch with us, and we're happy to help.
Okay. Thank you.
Bye.